Hello, very good evening. Am I audible? If I'm audible, please tell. Am I audible for everyone? Okay, I think I'm audible. Now we can start the class. Okay, so yesterday's class, I will tell you a few things. We have discussed about the applications of Gauss law. Application of Gauss law means to calculate. Very good, beta. Vamshi, Other. Good. Now, yesterday we are discussing the few things related to the Gauss's law and their applications. When we are talking about its application, means we have to understand how it is used in the various calculations of electric field. So, calculation of electric field due to suppose a spherical charge is there. Okay, spherical, we are taking a conductor, or maybe at the spherical cell only, or we are taking a solid sphere, is a non-conducting solid sphere, then also we are calculated that part. That's the second question. After that, for point charge also we have calculated, and then we have calculated for a line charge. So this was the last question we were discussing. If it is a line charge is there, and this linear charge density, if you are taking it, it is given to you that a linear charge density is equal to lambda. We are putting it as a linear charge density lambda, and due to this lambda we want to calculate at a distance of r what is the electric field. So we have seen the closed integral of E dot ds into q enclosed by epsilon, and using this concept we have got the result that is equal to lambda by 2 pi epsilon r. And curve, if we want to see that E versus R curve, if we are drawing it, this is E inversely proportional to R. This was the basic thing we have discussed. Okay, I think it is clear to everyone. You can watch. If you have not watched the last class, you can check it, and in that class you will understand the complete derivations I have covered there. Now we are going to move to the next part. What is that, beta? Try to understand it. Very simple thing. If I am saying this is the E versus R, but this is for line charge. That means very thin line is there. Very thin line, just like thread. On a thread we are saying there is a current charge is present. Okay, using that we are calculating this part, and we done this calculation that we call it what, beta? Electric field calculation. Now we are taking to you the next point, next consideration. I am telling you, suppose this is a spherical cell. Sorry, spherical cell we have done, that the plane sheet I am talking about. This is a non-conducting plane sheet, infinitely large. It's a large plane sheet is there. It is a large non-conducting. It is a non-conducting, beta. Okay, uniformly charged plane sheet. What I'm telling you, just remember this basic thing. This is not conducting. Conducting we will learn after some time. Okay, this is the conducting. Non-conducting, this sheet is there, and it's the large, or not a small sheet we are taking. Okay, so the large sheet is there. So on this surface, if you take the charge, suppose I'm taking a positive charge, you can take negative also, no problem. This is the charge is there, and surface charge density given to you sigma. What is given to you? Surface charge density sigma. So using this sigma, now we are going to draw. We have to solve this part using Gauss law. What is the electric field? What is the electric field? Sahibaz beta. Okay, this we want to calculate it. So how to calculate the electric field? I am taking here Gaussian surface. I am taking it the Gaussian surface here, cylindrical Gaussian surface, and I am taking this side also. This is the Gaussian surface. It is going on. What is the meaning of this? Please understand it. Please understand this thing. I will take you one basic part that would be more clear to you. Just give me 1 second. I will show you. Paper. Suppose this is a very basic example I am telling you. This is suppose plane sheet. It's a very large, by the way. So for our understanding, I am taking it the plane sheet is there. If anything written on it, just ignore that part. Don't go for it. This is a plain sheet is there. So on this plain sheet, I want to calculate nearby to this plain sheet, what is the electric field. So we are taking a what? Gaussian surface. So I'm taking a cylinder. So this side cylinder, if you see this cylinder, and similarly one more cylinder is there, second side, this part. That means these cylinders are like this, both sides. So this plain sheet is there, and both sides there the one cylinder is there. That means this same cylinder is coming out from both sides. That's the very basic. Understood? That we are taking it, that we are saying about with a non-conducting plain sheet. So I have drawn this cylinders one side and behind also this is cylinder, because this is a 3D figure, so it is little difficult to understand. Now I think everyone is clear about it. The plain sheet you are taking and both sides cylinder is there. Okay, symmetrical. Whatever size of this cylinder, the same size here you are taking it. Now suppose this area I am saying this is delta S. Okay, this is the delta S. So simultaneously it is also delta S. No need to say it is also delta S. No doubt about it. Okay, this is both sides. Now try to understand it. How many surfaces are there? So I am taking there are 4 surfaces. What are the 4 surfaces? This is surface 1, this is surface 2, this is surface 3, and this is surface 4. What are the meaning of this? Surface 1 means this lid of the cylinder. Okay, Gaussian surface. And this second surface is a curved surface. This curved surface of cylinder. Okay. Similarly, third also curved surface. And fourth is again lid. Then there are 2 cylinders are there. So there are 2 lids and 2 curved surfaces. So I am putting it curved surface 2, curved surface 3, curved surface. Okay. And these are 2 lid 1 and 4. These are lid. Okay. I think this is a diagram is clear to everyone. Now using this diagram, we can draw it what with a very simple calculation of electric field we want to calculate. Surface 1 if you see, because this is a one charge, plain charge sheet is there, and in this sheet this is a positively charged. So field would be radially outward. That means outward direction the field would be this like this. It is a field. Here also field is radially outward. This is behind the scene. That means this is also backward side. That is the field. This is also backward side field. Okay, if you are not understanding, I will tell you. This is a very suppose this seat is there. So this side field would be left side and right side. For me, for you, this would be left by the way, and this side would be beta for me left, and for you this is the right side. So their field is there that you can put it. So one side left, one side is right. So this field would be both sides outward direction field is there. So I am drawing it. This is outward side direction field. This is E, this is E, this is also E, E and T. Got it? Now please understand. Now area vector we have to see. What are the area vector? For 1 this is area vector. For 2 this is area vector. For 3 also area vector. For 4 this is area vector. These are n caps that we have to understand it. Okay? Now focus on the board. You will say very simple, it's a closed integral E dot ds is equal to Q enclosed by epsilon naught. Q enclosed by epsilon naught. Shari beta, hello. Now we have to solve it. So how we can do? We can break this closed integral, means closed surface, into the 4 surfaces. So what you will say? Integration of for surface 1 E dot ds, okay, plus surface 2 also E dot ds. Similarly for surface 3 also E dot ds. Okay, you can write it. Similarly for surface 4 also it is E dot ds. You can write it, and that is equal to Q enclosed. So how much is enclosed? Enclosed charge is this parallel region. What is the area? Delta S. What is the sigma? That is sigma only. So directly you will say charge is equal to surface charge density into area divided by epsilon naught. I think it is clear to everyone. It is clear beta? Now if it is clear, then we can solve this question very easily. What you will see in the surface 1. In surface 1 E and ds both are in same direction. That means both are in same direction means their dot product would be EDS only, because EDS cos 0 is equal to 1. So directly you can say for surface 1 this would be EDS. Okay, now come to the surface 2. Surface 2 E and n cap both are perpendicular. So their angle between them, that is a 90 degree. Cos 90 is 0. That means here this dot product is 0. Similarly, for third part also, here E and N cap, they both are also perpendicular. Again, the answer would be 0. Now, fourth case, if you are taking it, here E and N cap, both are parallel. Again, angle between them 0. Cos 0 is equal to 1. That means again I can write this is surface 4, that is equal to EDS. That means EDS is equal to sigma into delta S by epsilon. That is a very simple thing. Now take surface 1, surface 2, surface 4. Because the field is a outward direction and is a constant in this area. That means E can be taken outside. You can say that for surface 1 ds. Similarly, E for surface 4 also ds is equal to sigma into delta S divided by epsilon. Now surface 1, what is the area? The same area delta S. Surface 4 also area is delta S. So you can say E into delta S, same for E into delta S, is equal to sigma into delta S by epsilon. Delta S can be taken common. This becomes 2E. That means E is equal to, you can write E equal to beta sigma by 2 epsilon. It is the electric field. And definitely this electric field is perpendicular to the surface. If you want to write vector form, the better is to write like this: E equal to sigma by 2 epsilon n cap. N cap means perpendicular to this surface. Perpendicular to this surface. This is clear to everyone? Yes or no? Please reply. Cherry, Sehbaz, Vamsi Yadav and other persons. Please reply. It is clear? Okay, this electric field we can write like this. Clear? And if you want to draw the graph also, E versus this R distance, means whatever distance from this seat we are taking it. So this would be approximately constant for R until unless it is become nearby only. Okay, if you are taking very far away, that means this seat is not become now large, then this field will not be constant. But if you are taking a infinitely large seat, then it would be constant value, and that is equal to sigma by 2 epsilon. Madhusmita. Okay, it is clear to you. Other persons also please reply. Is it clear or not clear? Cherry, Sebas, Vamsi. It is clear, beta? Okay. Now we can use this same concept for the conducting seat. It is a non-conducting seat, large non-conducting uniformly charged plane seat we are taking, and similarly we can write it for a non-conducting seat. For what seat, beta? Conducting seat. It is a non-conducting seat already, so we can see for a conducting seat. But when we are taking conductor, so what is the meaning of conductor? Conductor is having one special property. What is the special property? Suppose this is a conductor. If this is a mobile is there, if I am assuming it is a conductor, then what will happen? Try to understand it. This side also and this side also. Both sides. This we take is surface. What we take it? This is surface. It is also surface. It is surface. It is also surface. Both sides surface. But between this thickness, little thickness, you can see that we call it bulk. Means inside this conductor, the field would be 0. The charge present only on the surface, charge present only on the surface, but inside charge is 0, inside field also 0. So remember this thing, that means inside field is 0, outside this surface is there, one surface here. For one surface, what is the field? Just now we have calculated sigma by 2 epsilon. Sigma by 2 epsilon, try to understand it. This is sigma by 2 epsilon, this side also sigma by 2 epsilon. We can use it and we can calculate the field anywhere. I am telling you. Now come to the next point. Prove to beta. Now try to see. Suppose this is a conducting seat is there, beta. It is the conducting seat is there, beta. This is a conducting seat. This is a conducting sheet. It's a surface charge density that we are again taking as sigma. So why I'm making little thick? So that's the simple reason is that this is the one surface and this is the behind is also one surface. But between part we call it bulk. What we call it? Bulk. Try to understand it. So I'm writing here that the charge conducting, it's the charge conducting large plane sheet. Large plane sheet, that means infinitely large plane sheet it is, that we want to calculate it. So if we see this picture clearly, I am taking the side view now. So side view would be like this, it would be look like this. It would be look like this. Okay, this is look like this. This is very large. So this thing is very far away. So try to understand. Very large. So this side also charge is present is here. This surface also charge is present, because here we cannot see, but we know here this is also sigma, it is also sigma. So this is one plane surface only. It is also one plane surface. So due to this surface, I am saying suppose this is surface 1, this is surface 2. Okay, this is surface 1, this is surface 2, and due to surface 1, in previous slide we have calculated already what is the field, sigma by 2 epsilon naught. What is field? Sigma by 2 epsilon naught. So using this same concept we can calculate again. Ki sir, here we can write due to 1 the field, because it's a positively charged, there would be field again E1 and that value is sigma by 2 epsilon naught. It is a positively charged. This is due to 1 I am writing it. Similarly, due to 1 this side also field is there. You can write it. This is also field, or this side also field. This is also sigma by 2 epsilon naught. It is the E1. This is also sigma by 2 epsilon naught. It is also E1 that I am writing it. That means this is the field due to the sheet 1. Similarly, you can see due to the sheet 2 also there is a field. Sheet 2 means this is a positive. So due to positive, field is also radially outward. That is the E2. That is equal to again sigma by 2 epsilon naught. Here also this is right side now. This is the again field is this direction beta. This is also sigma by 2 epsilon naught. Here also this is a positive side. That means here also the field is what? E2 is equal to sigma by 2 epsilon naught. Now please understand and tell me if this is the picture is clear or not clear. This is E. Red color I am writing due to the surface 2. The yellow color due to surface 1 we have written. Now you can see one side. If I am taking this is region 1. This is region 2, this is region 3. In region 1, region 2, region 3, we want to calculate the field. We want to calculate the field. How to calculate that field? Try to understand it. You will say very simple, in region 1. Region 1 beta. If you see region 1, this region, both field in same direction. That means they are added. So what is the net field? So you will say E equal to E1 plus E2. E1 plus E2 means sigma by 2 epsilon naught plus sigma by 2 epsilon naught. So this becomes sigma by 2 epsilon naught, sir, plus sigma by 2 epsilon naught, and total becomes sigma by epsilon naught. Of course, it is also radially outward. So you can write very simple thing. This field is equal to, can be written like this, sir, equal to sigma by epsilon naught n cap. N cap. N cap. This is due to region 1. Now similarly you can see the same thing in region 2 also and region 3 also. If region 2 you are writing it, you check it directly, you can tell region 2 both field in opposite direction. So they are cancelling each other. That means this field is equal to 0. And just now I told you also property in conductors the field net field is 0. So inside the field region 2 should be 0 and it is also mathematically also 0. Region 3. If you see the region 3, what is the field beta? This side both field are added. Both field are added. That means E1 also, E2 also, sigma by 2 epsilon naught, sigma by 2 epsilon naught, you add it, this becomes sigma by epsilon naught. So you can say E equal to E1 plus E2. Again you can write it, that means sigma by 2 epsilon naught plus sigma by 2 epsilon naught. E equal to beta sigma by epsilon naught, and n cap. This is also very basic thing, perpendicular to the surface. So due to conducting sheet, what is the field? Sigma by epsilon. Due to non-conducting sheet, what is the field? Sigma by 2 epsilon. I am repeating again. Due to conducting sheet, sigma by epsilon. Due to non-conducting sheet, it is a sigma by epsilon. Okay, conducting sigma by epsilon, non-conducting sigma by 2 epsilon. Very basic, you have to remember it. It is clear to everyone, beta? Vamshi, Shehbaz, Cherry, Boruto, Madhushmita, this is clear to everyone? Another person also in the viewer list, you can tell it is clear or not clear, beta? Letters. Which color you are not able to see, beta? I will write it again. Santhu B, please tell which color you are not able to see. That letters I will write again. White color or yellow or red? Please tell, beta. Or you can increase your brightness. Red color. Okay. I am changing the colors. That no problem. I will change. Okay. This I am changing. No problem, beta. You can increase also your brightness, but I am changing it. Better to green I am taking. Green is visible now. You can check it. This is the outward direction. This is the E2, that is equal to sigma by 2 epsilon naught. Here the E2, that is also sigma by 2 epsilon naught. Here also E2, that is equal to sigma by 2 epsilon naught. We are writing it, and here you can take another color I am taking again. This is the region 1, region 2, and this is region 3. Now it is clear, beta? Okay, now it is okay. Shantu? It is clear now, beta? Shantu B, beta, please reply. And other person also you can reply ki it is clear, it is visible colors or not. Okay, I think it is clear. Now I am taking to the next topic, that is the dipoles. The one very important topic, that is the electric dipoles. Today we are going to discuss that part and we will go into details. Okay, what are the electric dipoles? Okay, listen carefully. Electric dipole. Why we are studying first thing, that is a very important thing. Please focus and understand that part. When we are saying dipole word is not actually any new word for you. In chemistry, in the 11th class also, you have listened very carefully. In different chapters, there the dipole word is there. Where you have studied, I will tell you. There the one term. Welcome, beta, Santhu. That is a very simple term they are using. Ki there are some molecules are polar molecules, some molecules are non-polar molecules. Just like water, if you take it, it is a polar molecule. If you take the carbon dioxide, is a non-polar. So just like that, you have seen the some this type of words you have read in the 11th class, also in chemistry. So there are some polar molecules are there, and they have little different kind of properties, and they show some different chemical properties, some physical properties. So I'm not going right now in those properties, chemical properties and other part in chemistry part, but I'm telling you there's a polar word is there. When we are saying polar word, so what is the meaning of that polar word? Polar word, if you see it, suppose I'm giving you very simple, suppose HCl is there or NaCl is there. This type of molecules are out there, sir. So they are having some polar kind of properties are there. Okay, but if you are taking suppose H2 molecule is there, Cl2 molecule is there, O2 molecule is there, or N2 molecule is there, they are not having that kind of properties. They are not polar, so they are non-polar. So what is the meaning of that? Meaning is very simple. If you see it, you will understand. Suppose I am saying this is the H2 molecule, beta. So H2 molecule means this is the H and this is H, and they are separated by some distance. Okay, or you are writing suppose Cl2, so you are saying this is Cl atom and this is also Cl atom, they are separated by some distance. Okay, and you are saying suppose O2, O2 is a very simple, this is a O and O, they are separated by some distance. This is a very simple chemical structure I am going to. Don't try to check their bonds. I am not teaching here chemistry. So don't try to check their bonds. I don't know. I am not going into that part. Now, but there are some other examples also. Suppose I am telling you HCl is there. So if you draw this HCl, you will draw like this HCl. If I am saying draw the HF, so you will draw again HF. Okay. If I say here draw CO, again you will draw like this CO. CO. Okay. This is a few basic examples again I am giving you. Now please understand one by one, you will see carefully. When I am saying H2, H2 means these are H and H. Both are identical atoms. So both are similar atoms are there. That means neither we can say that this H, first H or second H is more electronegative. That means it is attracting more electrons. Not like that. That means both are similar. That means charge is equally distributed. So charge at the center. Okay. So charge, we can say center of charge at remain at center. So any atom we cannot say it is a positively charged or it is negatively charged. No. So they are neutral. Like that is happening. But when you see these last three examples, this is example 1 or 2 or 3. These last three example, if you see in HCl, Cl is having a more electronegative nature. That means it attract the more electrons. So it becomes little negative and it becomes little positive. Similarly, it is also fluorine is also more electronegative. That means this is also slightly negative and this is slightly positive. Similarly, in CO also, oxygen is more electronegative, that is means slightly negative and this is slightly positive. This is happening. Now, this type of molecule we call polar molecule. Their properties is different from the first three properties, first three molecules. So, these properties we have to learn it in chemistry, but they have in physics also some significance. What is the significance? Because when you are putting these equal and opposite charges, just see it clearly. Del positive, del negative, del positive, del negative, del positive, del negative. And they are in molecules, that means their separation is very small. So when they are two equal and opposite charges are placed at a very small separation, we call electric dipole. What we call it? Electric dipole. So what is the definition of electric dipole? When, or we can say very simple, it is an arrangement of it is an arrangement of two equal and opposite charges placed at a small separation. So this is the very simple, we call it electric dipole. So electric dipole definition is very simple. So this is a very simple thing in the nature where you see the dipoles, I told you. Now try to understand it. So they are, suppose I am saying these are 2 point charges. These are 2 point charges beta. And this is suppose negative charge and this is suppose positive charge. One is negative, one is positive, equal and opposite. So if you are putting it and it's placed at a small separation, this arrangement we call it electric dipole. What we call it? Electric dipole. Electric dipole beta. I think it is clear to everyone. It is electric dipole. When I am saying this is electric dipole, now try to understand it. One is negative, one is positive. So if I ask you what is the total charge on the dipole, if I ask you Q total, when I say Q total, so that is equal to 0. That is equal to 0 because minus plus, if you add it, that becomes 0. So this is a very simple thing, total charge is 0. But when we say the charge of dipole, just remember this thing, charge of dipole or electric dipole, we are saying it. So what is the meaning? That means we are asking only, positive charge. We are asking only positive charge. That means Q value. We are asking only Q value. We are asking only Q value. Okay, only one Q. You have to tell it. Now, one more term we define it, that we call it electric dipole moment. What we define, beta? Electric dipole moment. Electric dipole moment. Electric dipole moment. So when I am saying electric dipole moment, what is the meaning of this? Meaning is very simple. We define one term that we denoted by P. And this P term is nothing else Q into D. Q into D. Q into D. Q is the charge. I told you the charge of dipole. That is the Q. And D is the separation between these charges. So separation between these charges will be called D. But this is a vector quantity. What is this? It is a vector quantity. Vector quantity means it is having magnitude also, direction also. So magnitude is very simple, D, that means separation. But what is the direction? So its direction is from negative charge to positive charge. What is direction? Negative charge to positive charge. That means if you draw this thing, these are positive, negative charge, and this is positive charge, then dipole direction. If you see the dipole direction, the direction would be here to here. This is the direction of dipole. This is direction of dipole moment. It is direction of dipole moment P. It is clear to everyone, beta? Sattu? Another question, please reply. It is clear to everyone? Direction is minus Q to plus Q. Please reply, beta. Is it clear or not clear? Okay, beta. Now we have to put it and we have to calculate it. RJ, beta, any tips for remember? What you want to remember it? Please tell, beta. First tell me your problem, then I will go for it. I will explain it. Now we are saying electric dipole in external uniform electric field. Uniform electric field. Very simple thing. Very first thing. Beta, whole derivation when you are talking it, very simple. I will say class 12th physics derivations. Very basic. First listen classes carefully. Okay, listen first classes carefully. You have to listen classes. Without that it is not possible anything. So if you are listening classes, then you will understand how the teachers is writing those things, those derivation. When you are understanding carefully and then write the derivation, and when you go to the home, just suppose today the teacher is doing 1 or 2 derivation or 3 derivation on a board, you have complete your notes. After that you reach to your study hour time, maybe in the home or hostel, wherever you are staying it. At that point of time, you have to read first your notes carefully, read it, close the notebook, now do the same derivation again. Same, just write it. Wherever you stuck, again check it. This is process you have to follow at least 2 times. When it is done, then after 1 week, just do the whole derivation in 1 week, whatever you have learned, and Sunday or Saturday, one day, keep it and just finish again the same derivation. You can write again, and before going your unit test, maybe okay, in a maybe month, you write it, and maybe then after that you are having midterm or midterm exam and final exam. Before that also just do 1 or 2 times the derivation. You write it, write. If without writing you cannot understand it, you will not remember it, you will forget. Okay, I think it is clear to you. This is the electric dipole in external electric field. Uniform, but remember this very important term is uniform. It is not uniform, then case would be totally different. So I'm first going for a uniform external electric field. This is the uniform electric field is there, beta. This is a uniform electric field I'm taking it. And this field is equal to E. I'm taking this field is equal to E. In this field, I'm putting a one dipole. Suppose I'm putting a one dipole that is equal to minus Q, and this is plus Q, and this separation, this angle I'm taking at theta. I'm taking this angle is theta. Okay, and this suppose center of dipole, and this separate distance is A and this is A. That means very simple. That means separation between charges I'm taking is 2A. So if I ask you what is the dipole moment, so you will say Q into 2A. So try to understand it. This is the very simple P direction, P value. So dipole moment is nothing as Q into 2A, that we can write it. Now using this part, now we can solve one thing. What is the net force on this dipole? And what is the torque acting on this dipole? What is the motion would be there? It is a translation or rotation. What is the acceleration? That those type of question comes to you. We have to solve one by one. Very first question is what is the force acting on the dipole? So first I am calculating the force acting on dipole moment. Force acting on electric dipole. Electric dipole beta. So when I am writing the force acting on electric dipole, at that point of time what you can do, you can understand it. This is the minus Q, it's the plus Q. We know there's a plus Q and this is a field. So in a charge, the force would be in same direction of field. That means this is the QE force is acting. And similarly, if you see in the negative charge, the force will act opposite to the E value. That means this is also QE value because charge is same, but this is in opposite direction, that is the QE. So this is also plus QE and this is also QE, but they are opposite direction. So if I ask you what is the net field, you will say the net force, the net force is equal to 0 because they are cancelling each other. They are cancelling each other. So this line is clear to everyone. This is clear now? The net force would be equal to 0. RJ, Santu, and other persons, you can reply and you can tell. It is clear, beta? This is the net force is equal to 0. If net force is 0, the second question comes to you. What is the acceleration? So no need to say what is the acceleration. That acceleration is equal to 0. Acceleration 0 means no translation. No translation. But no translation. There is one very simple concept is there that you have to understand it. If it is already moving with some speed, it will remain same. That means because there is no force, that means no acceleration. That means it is not moving anywhere. But if it is initially rest, but it is moving with some velocity, that it means it will move with the same velocity because there is no force. It is not going to change it. The velocity will remain same if it is initially having some velocity. But if we are taking electrostatic condition, means we are keeping initially at rest, means it will remain at rest. That means there is no translation. Now come to the next case, that the torque acting on electric dipole. It's a very simple thing. The torque acting on an electric dipole. That is the question. This is electric dipole. Now my question is that what is the torque? So how to calculate the torque? Very simple thing. Try to understand it. So this is the force. This is also force. If you see here, I'm just drawing this part. Just here I'm drawing again. You can see this is the part is there. There's the one force. This is the QE beta. This is the force. This is also QE. Okay. Here to here, if you're seeing, this angle is again theta. This total length is 2A. So question is very simple. We have to calculate the torque. So torque about, you can write this point is A, this point is B. Any point you can take it, this point is O. Remember one word I'm telling you here, very important statement. It's related to the mechanism, but you have to remember here also. If the net force acting on a body is equal to 0, listen my words carefully. If the net force acting on a body is equal to 0 and their line of action are different, if their line of actions are different, this is acting in this line and it is acting above line, They are not same. They are parallel, not same. So remember this thing. I'm repeating again. If the net force acting on a body is 0 and their line of action are different, then the torque acting on a body is independent of the point of origin. It is independent of point of origin. Point of origin means about which point you want to calculate. Your choice. You can take any point. Torque would be same. Torque would be same. Try to understand what I'm saying. Again, if the net force acting on a body is equal to 0 and their line of actions are different, then the net torque acting on a body is independent of line of action. So line of action means you can take about any point. Suppose I am taking about this A point. So torque due to this QA value would be 0. QE value would be 0 because this force is acting on A only. So this above QE force will exert a torque. So how much torque? That perpendicular distance. How much is perpendicular distance? This is 2a, this theta, that means this is 2a sin theta. So directly you will say, so torque is equal to what beta? QE into 2a into sin theta. Okay, 2a into sin theta. And this is r cross f. R vector in this direction, f is this direction, r cross f, that means this is the clockwise torque. It is the clockwise torque beta. Okay, clockwise torque. Now you can write properly. This is torque is equal to, you can say Q into 2a, one term. This is E into sin theta, and this is clockwise. Try to understand. Q into 2a, that is nothing else P. We have already written. That means you can say torque is equal to, sir, PE into sin theta, that we can say clockwise. Clockwise. So this is a very simple thing that you can write it, or you can write torque is equal to P cross E. That we can write it P cross E. I am proving it also, you will understand it. Carefully, listen carefully. This was the field. This was the field. Okay, and this was the dipole beta. Minus Q, this is plus Q. If you see carefully, you can say the dipole was this direction. It was the dipole direction. This is P, this is E. That means this is direction of E, this is P, this angle is theta. So P cross E, that is the clockwise. That's why I have written P cross E, not E cross P. So torque is equal to P cross E. This is the torque acting on this dipole. It is clear to everyone, beta? Is it clear? RJ, Manish, Shanthu and other persons, please reply. Is it clear? Is it clear to everyone? Now try to understand it one more thing. So torque you know. So I am taking to the next slide, you can understand it here. What is the torque? Torque we are writing torque is equal to PE sin theta. When I am writing torque is equal to PE sin theta, okay, now we can say case 1. Case 1, if I say theta equal to 0 degree or 180 degree, in both cases, if we are putting theta equal to 0 degree or theta equal to 180 degree, sin 0 also 0, sin 180 also 0, that means torque is equal to 0. Torque equal to 0. And this we call equilibrium position. What we call it? Equilibrium position. So that means theta equal to 0 and theta equal to 180 degree, these are equilibrium position. I am explaining in detail. Listen carefully. At first case I am telling you at theta equal to 0 degree. If you say theta equal to 0, directly you will say the torque is equal to 0. That means equilibrium, no problem. But listen carefully. This was the beta field. This is the field. This I am saying field. In the same direction of field, if you are taking it what beta? Dipole. That means dipole direction also same. Dipole also in same direction. This is dipole. So dipole moment and field both are in same direction. Both are in same direction means theta equal to 0 degree. And this position we call it stable equilibrium. what we call it, stable equilibrium. That we call it stable equilibrium, beta. Clear? Now come to the second case. Second case, I am talking about at theta equal to 180 degree. If I am putting theta equal to 180 degree, again here also you can say the torque is equal to 0, beta. Torque equal to 0. Just now we have proved here. So torque equal to 0 if you are putting it. Now what is the meaning? If you draw the picture would be like this. It is a field, beta. This is field. And dipole moment is opposite direction. This dipole is placed like this. It is a dipole. It is placed like this. What is the angle between them? 180 degree. What is the angle between them? 180 degree. 180 degree means torque is 0, but this is not stable equilibrium. This is unstable equilibrium. It is unstable equilibrium. It is unstable equilibrium. It should be clear to you. These are two cases. Now come to the case second. Okay, if I say the theta equal to 90 degree, if you put theta equal to 90 degree, so what is the torque? Torque is equal to PE into sin 90. Sin 90 degrees. What is sin 90? 1. So what is the torque? Maximum value. Now you will say, sir, why you are saying maximum? Because sin theta maximum value is equal to 1. What is the sin theta maximum value? 1. Minimum value is minus 1. So maximum value is plus 1. So this is a plus 1. So maximum value is equal to beta plus 1, that is equal to PE. This is the maximum value, beta. That's the very basic thing. So this is the maximum value. When it is minimum means 0 degree here given to you or 180 degree given to you, you can put it, you will get the answer. Is it clear to everyone, beta? Swati, RJ and other persons, please reply and tell me, is it clear to everyone? Is it clear, beta? Okay, I am assuming it is clear to everyone, beta. Now this is a torque we are saying, or force we have listened carefully when you are putting in one dipole inside the external uniform field. So how to calculate their torque, or how to calculate their we can say force acting on the dipole in uniform field, we can write properly. Okay, now another case I am telling you, very simple, listen carefully. Okay, very simple case I am taking it. Suppose there is one dipole is there. This is a external uniform field, and in this there is one dipole is there. This is any dipole is there, and this angle is theta. Dipole is there, and now you are rotating this dipole by angle d theta. So what is the work done that we want to calculate it? Work done in rotation of work done in rotating a dipole, an electric dipole. That's the question. So how to calculate? Because force is 0, so you cannot calculate the translatory work done. So what you can calculate? Rotatory work done, you can write it. So what is rotatory work done? So you will say work done is equal to dw is equal to t into tau into d theta. That means their torque is there and you are rotating by angle d theta. Tau into d theta, you can put it, you will get the answer. Now you will say tau. Tau is what, beta? Pe sin theta into d theta. You are rotating by d theta. Already torque is Pe sin theta, we have proved already. So you can say that dw is equal to Pe sin theta into d theta integration. Suppose you are 0 to w you are writing, and this is theta 1 to theta 2. So you can say the work done is equal to, this is Pe, integration of sin theta is nothing else minus cos theta. So you can say minus cos theta, beta. So minus cos theta from theta 1 to theta 2. Okay, theta 1 to theta 2. So I am taking to you next slide, you will understand it. You will say directly, if the work done is equal to, minus sign is outside at the Pe, and this is cos theta 2 minus cos theta 1, this is the limits we are putting it. Or you can say work done is equal to PE into cos theta 1 minus cos theta 2. That's the very simple case K. To rotate a dipole, electric dipole in external uniform field, this is the work done you have to do. This is the work done you have to do from theta 1 to theta 2. I am taking few cases also, very important cases in the PYQ question. There are a lot of questions are here based upon this. You will understand. Very simple case I am taking it. Try to understand it. Case 1. If I say if theta 1 is equal to 0 degree and theta 2 is equal to suppose 90 degree, that means 0 to 90 you are rotating and dipole. 0 to 90 you are rotating. In this case, that the question is again same. Ki what is the work done? What is the work done? So how to calculate the work done? Work done is equal to, you will say the PE cos 0 minus cos 90 degree. Cos 0 is 1, cos 90 is 0. That means this work done is equal to PE. That's the answer. This is the answer. That means from stable equilibrium to the 90 degree angle, if you want to rotate, that the work done is equal to PE. Case 2, I am taking to you. The case 2 is this, beta. If theta is equal to 90 degree to theta equal to theta 1 is equal to and theta 2 is equal to beta 180 degree. That means from 90 degree to 180 degree if you want to rotate, what is the work done? Second question. Okay, what you can do? You will say directly the work done is equal to PE cos theta 1 means cos 90 minus cos 180 degree. Cos 180 degree. Cos 90 is equal to 0. Cos 180 is equal to minus 1. So this minus become plus 1. So this become again what is the work done, beta? That is equal to again PE. Again PE. So work done here also you will get the PE. The case 3 I am taking to you. This is summation of first two cases. That means if I say if theta 1 is equal to 0 degree and theta 2 is equal to 180 degree, beta, you are rotating from stable equilibrium to unstable equilibrium. Theta 0 stable equilibrium, theta 180 that we call unstable equilibrium. That means stable equilibrium to unstable equilibrium you are going. So what is the total work done that we are want to calculate? How to calculate? Again you will say work done is equal to PE bracket cos 0 minus cos 180 degree. What is cos 0? 1. Okay, this is the 1, you can write it. And cos 180 minus 1. So you can say PE, it is the 1 minus 1, you can write like this. Minus it become plus 1. So 1 plus 1, this become 2. That means this become 2EPE, that is equal to work done. But if you observe carefully, case 1 and case 2, if you add both of them also you will get the 2PE. Because 0 to 90 PE, 90 to 180 PE, so 0 to 180 that is a PE plus PE, that become 2PE. Simple, you can get the answer. Got it? Please reply and tell me it is clear to everyone. Yes sir, no sir. This dipole case up to here, it is clear or not clear, beta? Okay, so this is a very basic case I am putting it. So what is a dipole? What is the dipole? Electric dipole is there. So if we are putting an external field, the what is the force acting on it, what is the torque acting on it, what is the stable equilibrium, what is the unstable equilibrium, what is the work done to rotate from stable to unstable or stable to 90 degree or 90 to 180 degree or unstable equilibrium. That basic questions we have discussed here, that is a very basic. Now move to the next point about this dipole I am taking to you. The next point is there, okay, if dipole is there, due to dipole we want to calculate the field. Due to dipole I want to calculate the field. That's the very basic thing that you have to understand. The electric field due to electric dipole. Electric dipole. Electric field due to electric dipole, very simple thing. So we are solving one by one, you will understand it, very basic. First case is on axial position. On axial position. On axial position. When you are saying axial position, what is the meaning of this? Listen carefully. Suppose there are two charges. This is the minus q, it is a plus q beta. This is the center of dipole, and this I am taking A, and this is also A. From this center of dipole, if you are observing it, you will see I am taking a one point here P, and this separation here to here I am taking this is R, and this R is value is given to you, and at point P I want to calculate the field. At point P I want to calculate the field, that's our concern. Got it? How to calculate it? Because there are 2 point charges, so we have to write the two fields. Try to understand it. So due to this positive charge, if I ask you this separation, so you will say, suppose this is a R positive separation. Here negative to this point P, I can say this is a R negative separation. I can write it, no problem. If I ask you what is the R positive separation, can you tell me the value of R positive? Yes. What is the R positive? This is R minus A. That means this is R minus A. If I ask you what is the R negative separation, so you will say this is R and plus A. That means R plus A. This is a very basic thing that you can write it. That means R negative and R positive values are like this. Now second thing, second concept that you have to learn it. What is the second concept? Concept is this beta, okay, at point P, due to this positive charge, field would be rightward direction, radially outward. This is field due to positive charge. But at point P, due to negative charge, field would be negative direction. That means this is a leftward action, radially inward direction, that is the E negative. That means if I want to calculate the net field at point P, that means we have to subtract, not add. We have to subtract it. So what we will say, you will say here that field, electric field at point P is nothing else E positive minus E negative. We have to do it. Now put the value. What you will say? You will say that this was the KQ. KQ. What is separation? R positive. R positive is means R minus A whole square. Minus. Similarly, KQ due to negative, R negative means R plus A whole square. Just observe this carefully. This is the field at point P. It is a field at point P due to positive charge KQ by R minus A whole square. Because KQ by R square, this is a field. Similarly, I am writing here. What you can do, beta, KQ can be taken common and you can take LCM here. What is LCM? R minus A whole square into R plus A whole square. Now you can take this side, this is the R plus A whole square minus R minus A whole square. This is the very basic. R plus A whole square minus R minus A whole square, that is the case. So we are saying this is EP. When I am writing electric field at P is equal to KQ, again you are taking common. You can write here, very basic case, focus carefully. This is the one quadratic, you can open it, okay, square function, that you can open it, this become R square plus A square plus 2R into A. Similarly, second also R square plus A square minus 2R into A. Okay, upon this is A minus B formula, this is A plus B formula, A minus B, A plus B, that means A square minus B square. That means you can say A square minus B square, and this both are square also, that means this is the whole square, we can write it. Just observe carefully, you will understand it. I am repeating again. R plus A whole square, that means R square plus A square plus 2RA. R minus A whole square means R square plus A square minus 2RA. Okay, minus 2RA. Upon R minus A and R plus A, that means R square minus A square. Both are square, that means this is a whole square. Is it clear? Now observe carefully. It is R square minus R square, A square minus A square, both is cancelled. 2RA minus minus become plus, that means this become 4RA. So you can say in the very next line, this is a KQ 4RA divide by, this become R square minus A square whole square, that is equal to electric field at P. Now observe carefully. Q into 2A nothing else P. Q into 2A nothing else P. That means you can write, so this is K. Here I can say Q into 2A altogether. What is remaining here? 2R is remaining. Okay, upon R square minus A square whole square, that is equal to field at P. I am writing little more. You can say very simple that field at P is equal to, this become Q into 2A nothing as P, that means K into P. 2 is also there, that 2R divided by R square minus A square whole square. This is the field on axial position. Important result, remember it. Important result, you have to remember it. What is the field? 2kp r upon r square minus a square whole square. Okay, that's the important result, you have to remember it. Now I am taking to the next slide, you will understand it. I can put here approximation also. What is the field we have written? That is equal to 2kp r divided by r square minus a square whole square. This is the one result we have derived. I am writing exactly same. Now I am putting one more thing here, beta. If approximation, what is approximation? If r is very much greater than a, in maximum question, 90% time this question is given to you in the paper, कि r is very much greater than a. At that point of time, what will happen? If you are putting this r is much greater than a, that means r square minus a square, it is approximately equal to r square only. Approximately equal to r square only, because this a square is very small as compared to r square. So when you are putting this thing, that means this field is equal to beta 2kp r upon, this become r square whole square, we can say. So r to the power 4, this is 1 r, so what is remaining? R cube. That means this 2kp upon r cube, this is the field on axial position, that you have to remember it. It is also very important case, but this case you have to apply when r is very much greater than a, otherwise you have to use this formula. Is it clear to everyone, beta? Is it clear, beta, to everyone? Now, okay, very good. Now this is clear to you. Now we can focus the another part. What is that, beta? We can go for it, that field on equatorial position. So I am writing it, electric field at equatorial position, equatorial point, at equatorial position or a point, that we are going to solve it. How to solve? Try to understand it. Suppose this dipole is there. Again, this is a minus q, this is a plus q. Okay, and you are taking a one point here at distance r. It is a, it is a, this point is o. This point I am taking it, this point is p. This point I am taking it, this is a p point. So at p point I want to calculate what is the field. What is the field? So how to calculate? Please focus carefully. You join this p point from q, similarly to minus q also. If you see this point, this is the r positive value, this is the r negative value. This is the r positive distance, this is the r negative. By the way, both are equal also, no problem. Now focus. Due to this positive charge, field would be radially outward direction. This is E positive. But due to this negative charge, field would be in radially inward direction. That is the E negative. E negative. It is the E negative. Understanding? This is a very basic thing, beta. Jai Mata Di, beta. Okay, you are understanding this part. This is the E positive, this is E negative. If I take this angle is theta, so what you can say, there are two components. This angle is theta, that means this is also theta. This is theta, then this is also theta. That means this angle also theta. Because numerically E positive and E negative both should be equal. Why equal? Because separation same. Separation same. Second thing, what is same beta here? Another part is same, that means charge is also same. Charge is same, separation same means magnitude also same. I am drawing this part, I am not disturbing this diagram. You will see here. These are two fields. This is the two fields are there beta, and this is the case we are drawing it. This is E positive, this is E negative beta. This angle is theta and this is also theta. By the way, numerically both are equal. So you can say this is a E positive sine theta. Okay, and this is the E positive cos theta. This is E negative, that is also E negative sine theta. And here also E negative cos theta. This is very basic. By the way, E positive and E negative numerical value same. That means E positive sin theta and E negative sin theta, they are cancelling each other. So what is remaining? E positive cos theta and E negative sin theta. These two terms are remaining. Directly you have to add. So what is the net field? Directly you will say, so the net field is equal to E positive, okay, cos theta plus E negative cos theta. So you have to add it. By the way, both numerical values same. So directly in one line you can say कि E negative, E net is equal to 2 times of E positive cos theta. That means you have to calculate only one thing, E positive. If you know that thing, that means you can solve it. Now put the second thing. What is the value 2? This is the E positive value. E positive value would be how much? K, Q divided by R positive square. Very simple. What is the cos theta value? If I am asking cos theta, so you will say this is the cos theta. Cos theta term would be this is A and A by R positive. So you can say again A by R positive. Now solve it. What you can do? You can say sir E positive, E net is equal to K into Q into 2A divided by R positive. What is the R positive value? Can you tell me? Yes. This is under root of R square plus A square. So you can put it, this becomes sir under root of R square plus A square whole cube. That means you can say very simple, so E net is equal to K Q into 2A, that is nothing else, P divided by, this become R square plus A square to the power 3 by 2. That is the answer. This is the E net. And this is also in this direction. That means this direction means, what is this direction beta? See clearly, this direction means this direction. It is direction of this net field. Dipole direction is this. See clearly. Dipole direction is this. This is dipole direction. And field direction is this. That means both are anti-parallel. Opposite direction. Both are opposite direction. So field and what beta? Dipole is opposite in this case. So that is a value that you can remember. It is also important case. Important result you can put it. Now second question comes to you. If this R is again very much greater than A, then what will answer? Again I am putting it, if R is very much greater than A, then what will happen beta? Then you can say very simple, R square plus A square is approximately equal to R square. Approximately equal to R square. Means from here you can write it, very simple thing, E net is equal to Kp upon R square to the power 3 by 2. You solve it, then this becomes E net is equal to Kp by R cube. So if R is very much greater than A, that point of time you can write E net is equal to Kp by R cube on equatorial position. On equatorial position beta you can write like this, on equatorial position. On axial position you can write 2 Kp by R cube. Understanding or not understanding beta? Clear or not clear? And one more thing you have to remember, this equatorial position also known as broad on position. broad on position. It is a broad on position. And similarly, this axial position also known as end on position. Also known as end on position. This is a very basic case we have derived the what is the field due to electric dipole on its end on position or broad on position that we can solve it. Is it clear to everyone, beta? Is it clear to everyone? Please reply. Okay. Now we are going to solve at a journal point. Any journal point I am taking it. This is the dipole is there. Electric field at a journal point. At a journal point I am talking about. So when I am talking about a journal point, you will understand it. This is a minus q beta charge. This is a plus q charge. And if you are seeing any journal point here, journal point, this point is here. This angle is theta. This separation is r. This journal point. At this point, we want to calculate field. This point is P. So that is our concern to calculate it. So how to calculate that, you have to understand it carefully. How to calculate? Please focus. This is a dipole beta. This is a dipole. Okay. And this R, I am assuming it very much greater than as compared to this A. So we are taking this very simple assumption. If here given to you, it is given, we are assuming it R is very much greater than A. That's the case. Don't worry about it. So this is the case. Now we want to solve it at P point. What is the field? So what is the field that you have to write it? Just listen carefully. This P can be taken two component. One is along the R and one is perpendicular to R. I am writing again. This is the P was there, beta. This was the P. And this was the R position, beta. This is the R vector. It is the R and this angle is theta. This was the P. It is the P. This is P, this is the R vector. Now we have to take the component of P in two directions. One is along the R and one is perpendicular to R. So I am putting it, you will understand carefully. This is a P two direction like this. Okay, this is two directions. One direction of P, this would be P sin theta. And one would be in this direction of R, that would be P cos theta. P cos theta. Now tell me, is it clear to everyone? This thing we can take very simple two component. One is along the R and one perpendicular to R. Clear? Now come to this point. I am taking any point to remove the confusion. I am saying this point A. This point is A. If you see the point A, just check this P cos theta, this line, this is the R vector, this is the axial position. But for P sin theta, it is equatorial position. For P cos theta, axial position, for P sin theta is the equatorial position. That means you can say there are two field will come. Two field will come. What are the field will come? You can draw directly. There would be two fields. What are those fields? One field would be along this R vector. That we are saying axial field, that means R vector means ER vector. And one field due to P sin theta, it will come perpendicular to this R, but in opposite direction, because we know the in equatorial position field is opposite to the P vector, and that we call it E theta. What we call it? E theta. Very basic, you can put it. What is ER? ER means axial position or radial position. In ER position, what is the result? Result we already know. In the previous slide, we can directly use. This was the result. 2 kp by rq. 2 kp by rq on axial position. Use it. Directly you will say this is the P cos theta. On this ER we are writing. So 2k, in place of P you will write P cos theta. And upon what is distance R, that means rq. This is the radial position field. It is the radial position field. Second case is what, beta? P sin theta. It is the equatorial. So for that also you can check. This is a Kp by Rq. Kp by Rq. That the result you have to use. So similarly, E theta also you can write that is equal to Kp, but you will use P or P sine theta because perpendicular component we can take. This is the P sine theta divide by R cube. These are two fields that you have to understand it. So ER, E theta you are understanding. So you know both field. Now using this both field you can understand and you can calculate very basic thing, that is the E net. What is the E net beta? E net is equal to root over ER square plus E theta square. Then you can find the net field also. Very basic, that means E net is equal to under root. If you are putting it under root this part, so Kp by R cube taken common. This is the Kp by R cube taken common. Under root, what is remaining? Here remaining 2 cos theta whole square. So you can say 2 cos theta whole square plus sin theta whole square. Okay, so from here you can say E net is equal to, sir, Kp by R cube. This become beta how much? 4 cos square theta. That means I can say 3 cos square theta plus cos square theta plus sin square theta. This sin square theta here. This is 4 cos square theta. I break into two parts. 3 cos square theta plus 1 cos square theta. Why I am breaking? Very simple. Cos square theta plus sin square theta is equal to 1. That's why I break it. So this is the E net is equal to beta how much it become? Kp by R cube. That is equal to how much? 3 cos square theta plus 1. That's the final result that we call it E net. So there are two fields I told you. These are field ER and E theta. You can find it. This is the E net. It is beta E net. It is E net. This is the net field is there. Very simple. Very good beta. Mathala, that we can write it. And last thing we am telling you here, this angle is alpha. Suppose I want to calculate this alpha also, you can tell. What is tan alpha? So tan alpha would be two things. Perpendicular upon base. Perpendicular is E theta and base is ER. So you can say E theta divided by ER. E theta, we already know Kp by sin theta. Kp sin theta by R cube. This is Kp sin theta by R cube. Upon ER is equal to 2 Kp cos theta by R cube. So 2 Kp cos theta by R cube, I can write like this. Kp R cube cancelled. So this becomes tan theta by 2. Okay, so I can write that very simple. This is tan alpha is equal to tan theta by 2. So major portion of this theory of related to the electric dipole we have covered today's class. I think it is clear to everyone. Okay, is it clear beta to everyone? Okay, I'm understand. Thank you so much for your class, and I think today would be the last day for this program, and so hope so you understood and you enjoyed this program. Okay, thank you so much. Bye bye. Enjoy your time.